This is the last lecture on the cell buckling, and perhaps the last lecture on the subject. So, let us briefly recall what we have covered till now. So, we have covered the buckling of cell, axisymmetric buckling of cell, and after that we have covered the buckling of cell following the Donnell's equation. We have derived the Donnell equation from following a simplifying assumption, and then we have solved for the three cases. One case is axially compressed cylindrical cell, and then axial compression along with the external pressure or suction, whatever. And then the third one is subjected to torsion. We have demonstrated that even though there are certain simplifying assumptions are involved in all these solutions, but there are very few interesting facts that we have uncovered using this theory. That is, the for certain loading condition, for example axially loaded cylinder, we have seen that it reveals the closely spaced and multiplicity of mode, and they allow the modes to interact because they are geometrically coupled, right? And so there is a huge reduction of the critical load that is eventually will be captured in post critical analysis, right? However, we have also seen that this mode multiplicity is also a function of the mode of loading, and the same cylinder is subjected to lateral pressure, external pressure or suction, or the same cylinder is subjected to torsion loading, then it is no more imperfection sensitive. Okay. So, what the fact is, the essential fact is that the closeness of the mode and then post critical load drop, and subsequently experimentally obtained critical load and then analytically obtained critical load shows huge disparity. All these things are related. So, now what we are trying to do the analysis in the post critical regime, that means after buckling what really happens. So, for that we have adapted the similar approach as in in Donnell's equation, but then we have kept the equilibrium equation, out of plane equilibrium equation, and then the in plane equilibrium equation separate, and of course there will be our coupling. So, we have two field variable, one in W, that is out of plane deflection, and then another field variable is essentially the stress function. So, what we know that axial in plane forces can be derived from the stress function, and then the governing equation for the equilibrium as well as the compatibility equations we derived and we have written down, and then we are trying to solve it. Of course, because of the complicated nonlinear form of the equation, we are going to consider a simple panel, which is cylindrical panel. Okay, and this panel we are assuming, so this is subjected to axial force nxx in two directions, right? This is x, and along this y direction it is all simply supported. These are all simply supported. These are all simply supported, and all these edges are simply supported, except it is allowed to deform axially because of this axially loaded axial compression, and then z is perpendicular to that. Okay, z. So, the solution we are going to present is Volmir solution, right? This is simple ad hoc, but still it shows essential features. The Volmir solution we also adapted to solve the post critical behavior of plate. In that, essentially you will recall the steps involved. So, there we had two equations, one is equilibrium equation and another equation was compatibility equation. So, what we did, we assumed essentially some deflection profile, and then from the initial forcing initial initial state of stress, we derived some approximation of the stress function, and then we substitute in the equilibrium equation, right, because they are coupled equation, and then we solved using Galerkin. Essentially the same steps we are going to follow. So, we have also assumed that this is of length A, and in this direction this is also of length A. A is, so why both are A? Because of the simplification. Okay. Now, we assume, and also the another interesting thing, what we must consider the imperfections, right. So, if you can recall that in the previous class we have explained the inclusion of we have included the term of imperfection in the strain displacement relationship, right. and they are imperfections. So, the kind of imperfections that we are going to assume is similar to the buckling mode. Okay. So, these are eigen buckling mode or eigen mode have fine imperfection, fine imperfection. So, this is similar to the, except they differ by scaling factors. Okay. Please note that imperfections can be random as well, but that will quantitatively change it, qualitatively there will be no change, and we want to demonstrate the qualitative post critical load drop. Okay. So, as you see the assumption, so W, let us assume W is equal to W0 with this kind of boundary condition, sin pi x upon a, sin pi y upon b, right, pi 1 upon a, right. This is the deflection. Now, imperfection, I can assume imperfection W is equal to W0. I am assuming this is F, okay, and W0 is F0 sin pi x by a, sin pi y upon a. So, this is the deflection, okay, outward or out of plane deflection, and this is imperfection. Please see why they are self-affine, because this is similar in expression spatial distribution to that of the deflection, right. That is why they are, and F and F0 has the nothing but amplitude of F and F0 are the amplitude, right. Amplitude of the deflection and imperfections. Okay. So, with these assumptions, let us substitute in the compatibility. So, first let us use the compatibility equation. Okay. So, I am removing it. So, because the equation is a little big, large. So, the equation capital F is nothing but, so we are considering the compatibility equation. Okay. Compatibility, because we have assumed the deflection and imperfection, we need to know the stress function, because there are two variables. That is what we are considering compatibility, and F is the stress function. So, here we will write down the equation del 4y del x4 plus 2 del 4x del x2 del y2 plus del 4f del y4. This is equal to, from here I will write, okay, E del 2w del x del y square plus 2 del 2w0 del x del y del 2w del x del y minus del 2w del x2 del 2w del y2 minus del 2w0 del x2 del 2w del y2 minus del y0 del y2 del 2w del x2 minus 1 del 2w del x2. So, this is the governing compatibility. Okay. So, what we will do, we just take W and W0 and then substitute here. Okay. So, substituting W and W0 in this equation. So, if we substitute in this equation, you can clearly see that right hand side will be known, right, and when right hand side is known, right hand side will be expressed in terms of some kind of series of sine and cosine, sine functions, right. See, these are all double derivatives, so it will be all sinusoidal, right. And when you take product of sine, you can always express this in terms of addition and difference of sine function, right, because we know that 2 sin A sin B is nothing but cos of A plus B by 2 into cos A minus B by 2, right. Cos of A plus B minus cos B minus A, something like that, right. So, what we see the right hand side is a sum of sum of trigonometric function, sum of sines and cosine, sine function, right, sine functions. So, if the sum of sine functions, then you can see this is a linear differential equation and this is a fourth order differential equation, right. So, thus we can assume the series solution. So, what kind of solution we can assume? That f is consisting of maybe some unknown coefficients a sin pi x by a plus b sin pi y by b a pi y by a or something like that, right. And then we can substitute in this and then we equate the coefficients of sin pi x by a and sin pi y by b term. You see that? So, essentially we are doing a series solution. All of you have done this series solution, right, in differential equation. What happened is that you assume the solution to be in the form of series Ax. So, for a one dimensional equation, it is like alpha 0 plus alpha 1 x plus alpha 2 x square, something like that. And then you substitute in the equation and then in both the side you equate the coefficients associated with the x term, x square term, x cube term. Okay. The same thing you have done where you have done these things in your undergraduate. Let me remind you. You consider the Legendre equations. You consider the Bessel's equation. So, all these equations can be solved using the series solution. And then the kind of equations that you get, the Bessel function is the solution of the Bessel equation and then Legendre polynomials are the solution. So, the places where this technique series solution is particularly useful is the differential equation in which variable coefficients. Okay. But here it is not variable coefficients, it are all constant coefficients, but nevertheless it is applicable to here also. Okay. So, you once again let me reiterate, you take this function and then you substitute it. So, right hand side, this side become a function of the sinusoidal term, then you assume the solution to be series of the sinusoidal terms, okay, and then equate the coefficients you will get. So, I am finally write the stress function. So, you will get the stress function to be E. Okay, so if you substitute here, you will see if you substitute here, you will get E f square plus 2f f0 pi to the power 4 divided by 2a to the power 4 cosine of 2 pi x plus cosine 2 pi y upon a plus pi square f divided by r square sine pi x by a sine pi y upon a. So, by substituting this, so you see that this is cos, sine, right. So, similar unknown coefficients you can assume and then substitute and equate the coefficients and then equate the terms of all these terms. Okay. So, then if you do that, then you will see the solution for the one solution for f for the stress. F is nothing but the stress function, right. F will be, I am writing down, okay, is equal to E f square plus 2 f f0 divided by 32 cosine of 2 pi x upon a plus cosine of 2 pi y upon a plus E f square by 4 pi r sine y x y a sine pi y upon a. So, essentially what you did, you assume C1 cos 2 pi by a plus C2 cos 2 pi y by a plus C3 and then you substitute and you will get this. Do you see that? So, this and this similarly will have this kind of term, right. Okay. So, is that everything? No. Stress function, this is one of the solution and it is solely based on the assumed deflection profile and then associated imperfections profile, right. But it must have due consideration of the initial state of stress. right. So, the stress function must have due consideration of the initial state. So, the stress function, so the stress function must have consideration from the initial state of stress. Initial state of stress, right? Or initial state of in-plane stress. Stress means these are all in-plane stress, right? So, how to do that? Now, if you can recall that initial, so membrane stress is what? Minus Px into H. I am assuming that it is uh, this one is actually compressed in x direction, right? I am assuming that this is Px is the pressure per unit area. So, Px into thickness H is the force per unit length, right? Px is the pressure, okay? Axial compression pressure, huh? And then Nxy is 0 and Ny is 0, right? So, Nxx is what? Nxx is nothing but del 2f, del y2 is nothing but minus Px. H is the thickness of the cell, right? H is the thickness. So, you integrate it and then you will see F is will be minus Px H y square by 2 plus C1 y plus C2. Now, if you consider this term and this term, of course, this if constant stress function doesn't really give any stresses. So, it doesn't really relevant. This term, if you differentiate twice, this is also be 0. It doesn't give anything. So, only meaningful contribution comes from this, right. So, now this is one solution, maybe F1, this is another solution, right. So, what we have learned for any equations, right, then if so, we can treat this to be a particular solution, particular integral, and this is complementary function. So, total solution F is the particular integral solution plus complementary function, contributive function, right? Because it is a non-homogeneous equation, solution of a non-homogeneous equation is consisting of two terms. So, I can write, so if the total solution become f square plus 2f f0 divided by 32 cosine of 2 pi x upon a plus cosine of 2 pi y upon a plus e f square by 4 pi square r sin pi x by a sin pi y by a, and then this one is minus px h y square upon 2, right, the whole. So, this is the function of the stress function, right. So, now you see I am having the displacement profile d w, I have, but f and f0 is not known, f and f0 these are unknown, right. But we got a functional expression of f, w and w0, right. So, how to determine f0 you know, because f0 is what? The imperfection amplitude. If you do measurement, then you should know imperfection amplitude, right. But what you do not know is f, because f is the given the amplitude of displacement, right. So, how will you do that? Well, which equation we made up? We have satisfied stress compatibility, we have satisfied compatibility, we have satisfied the boundary conditions while assuming this kind of solution, right. Boundary conditions were satisfied, compatibility was satisfied to obtain the particular solution for the stress function. The only thing that is remaining is the equilibrium equation. So, we have to solve the equilibrium equation, but do you think that if you directly solve this f, if you substitute the stress function as a function of x y, if you substitute for w and w0, it will satisfy the equation? It will not, right. There will be some residual. So, the best way to do it using residual error technique, right, least square, Galerkin technique, Bubnov-Galerkin, right, to solve the equilibrium. So, let us solve or enforce enforce the equilibrium by equilibrium in a using Bubnov-Galerkin technique. Why Bubnov? Bubnov means the weight function that you are going to use will be same as the function you have assumed. So, what is the weight function? Weight function will be same as the whatever is associated with w pi x by a into pi y by a, right? That is the weight function. So, the error terms by substituting in the equation, substituting w and f in the equation, in the equilibrium equation, we substitute, then equilibrium equation, what you are going to get is, so you see that equilibrium equation, if you can recall what was the equilibrium equation, equilibrium equation was something like this. You see that del 4 w by del x4 plus 2 del 4 w by x2 y2 plus del 4 w del y4 minus h by d del 2f del y2 del 2w del x2 plus del 2w0 del x2 minus 2 del 2f del x del y del 2w del x del y plus del 2w0 del x del y plus del 2f del x2 1 by r plus del 2w del y2 plus del 2w0 del y2. That was the equilibrium equation, right? So, you substitute w, you substitute for f, you substitute w0, right? And then whatever I am assuming, that substituting w w w0 and f, okay. If substitute, there will be error term, I am assuming error epsilon, this is error. And what will be the weight function? Weight function, weight function for Bubnov-Galerkin weight function will be what? The same, the sin pi x by a, sin pi y by a, right? That's the error function. So, now if we enforce that error minimize, error minimize weighted least square, right? Weighted least square, what we do? You multiply the error with the weight function and make it 0 over the domain. So, integration 0 to a, integration 0 to a, epsilon x y error 1, and then weight function w x y must be equal to 0, right? So, here what we get, integration 0 to a, integration 0 to a, whatever is the error, I do not know, there will be big expression of error. It is better to do it in using Maple or MATLAB, using symbolic computation, that is better. So, sin pi x by a, sin pi y by a must be dx dy must be equal to 0. This by doing though, so from here, so that is one equation that will give you, from here if you simplify, then you will get the equation. So, then you will get from here, I will get the unknown is px, px will get, I am just writing the expression, f y f plus f0, and then 4 d pi square by h square plus e square divided by 4 pi square r square plus pi square E divided by 8 a square f square 3f f0 plus 2 f0 square minus 4e divided by pi square r 5 by 6 f plus f0. Okay. So this will be the, you see, this is the, please note that this Px is beyond buckling. Okay. So this Px is beyond buckling. So it can take both the critical as well as post critical regime, right. So what we are going to plot? Our alternative to get the equilibrium path here, right. So Px versus what? F. So we will plot Px versus F. F is the amplitude of displacement, right. Amplitude of outward deflection, out of plane deflection. So this is will give you the equilibrium path. So this is the equilibrium path for the cell. Say for the equilibrium path for the cell, cylindrical cell panel. I will not call it whole cell because I am considering a panel. For whole cell it will be more complicated, okay. But I want to demonstrate it, that how curvature is going to influence the load drop. So equilibrium path is the one from the very beginning. You will now you go back to the very few initial lectures, right. I was repeatedly emphasizing equilibrium path because that gives her all the information about the system behavior, stability behavior. Okay. So now I am going to plot it. Okay. So when I am plotting it, you please note there is a very important stuff here, that F versus Px versus the equilibrium path is a function of the imperfection amplitude F0. It will also be a function of the distribution of it. That means here we are assuming that this is to be self-affine, that means similar to that of displacement field, but it will have little imperfections. If you do a full scale finite element simulation, which are available in various research paper or journals published, we also have our papers. There you can see, but here at least a very important interesting thing we can see. So I am going to plot this thing for you. We can, there are some kind of dimensionalization that can be is possible. So some dimensionalization, okay. Dimensionalization, okay, non-dimensionalization, okay. Non-dimensionalization, so it will not have dimensions, okay. So if you do non-dimensionalization, then this is the way you will do Px bar. So Px is being normalized, so it is Px, whatever that Px we obtain, Px square by E h square, K is square by RH, delta is equal to F by H, and delta 0 is equal to F0 by H. So these are all non-dimensional. Please note that F by H, F is the amplitude displacement, H it is non-dimensional with respect to thickness of the cell, imperfection amplitude non-dimensionalized by the thickness of the cell. So these are the non-dimensionalized deflection, this is non-dimensionalized imperfection amplitude, right. And this K is a parameter which is essentially square by RH, okay. So is the length, so it's similar to Barth-Dorf parameter, right. L square by RH root 1 minus c square, right. It is similar to like Z parameter, which we have previously we have explained, right, which distinguishes between a moderately long cell and the short cell, right. And Px is the non-dimensionalized axial force, axial stresses. So then if you do, then final equations you will get Px bar if you substitute. Of course, this can be non-dimensionalized as pi square by 3 into 1 minus nu square plus pi square by 4 pi square plus pi square by 8 delta square plus 3 delta delta 0 plus 2 delta 0 square minus 4k, 4k, let us put it small k, okay, small k, 4k divided by pi square, pi by 6 delta plus delta 0 delta delta plus delta 0, okay. This will be, now you can clearly see that see when we consider the critical load if you can recall for the cylindrical cell, what it was for the axial force, if you can recall, nx 1 was what, nx was 1 divided by root 3 into 1 minus nu square, e eh square by r square, something like that, na, square by r, right, isn't it? But here you see that, so if you non-dimensionalize, you see that 3 1 minus nu square term is coming, right. So this term takes care of the buckling things. You see, an additional terms take care of the what is the post critical, what is happening there, okay. So now I am going to draw it, okay. So when I am drawing it, you please note that do you see non-dimensional is k parameter, k, because that is similar to Butler parameter, right. With that p bar I am plotting. So you see that if there is no imperfections, then you see that what kind of plot you can see. Of course, as you increase the displacement, as you increase the k bar, sorry, k bar means some kind of slenderness, measure. So it will decay, right? The way column decay with increasing slenderness ratio similarly. But if you put little imperfection, so this is for perfect cylinder. Please note that this is for perfect cylindrical cell, perfect. But as soon as you put little imperfections, then what is happening? It is going up, this is the point where it is buckling, because after that there is a decrease in the load carrying capacity. Do you see that? So from the equilibrium path itself, you will get this, right, that we have seen that which one is the critical load. Similarly here, what is the maximum load, that is the critical load. After that, do you see there is a decay? But what is most interesting to see here is that, for 20 to this one, there is a decay. You see that there is huge decay in the critical load, huge decay in the critical load. And why this decay in, why this significant, decrease in the critical load is because of imperfections. You see that? So, this really shows the imperfection sensitivity, imperfection sensitivity, okay, sensitivity, right. Now, and if you see this one, you can recall a little bit now here. I will go to once again initially when we have consider the cases for a simple system, right. Can you recall that where you can see this kind of imperfection this kind of equilibrium path? You can recall that we are having this one, there is this rigid bar, right, and it is restrained here by spring, inclined spring, and then it was subjected to some force P, right, and then we can clearly see, you have seen that on this side it was from here to here, and then so asymmetric, you know, asymmetric equilibrium path and stable unstable behavior. From this side it is stable, this stability unstable behavior. So, this was basically similar to this. So, you understand, although this system was hypothetical system, idealized toy system, but we now can see a system. At that time I used to emphasize that cell shows this kind of behavior, but do you see similar kind of equilibrium path you can see from here. So, this is stable unstable bifurcation, asymmetric stable unstable bifurcation, and when it is unstable it is imperfection sensitive, because there is a limit point, it is increasing and then it is decreasing. You can see clearly these points are called limit point, right. So, these are limit point instability, limit point. So, as soon as we put imperfections, the bifurcation instability get converted into a limit point instability, because this sudden in the perfect system transition from stable to unstable is not abrupt, okay. Here it attains maximum load and then it goes down. So, this is called limit point. So, whatever we have discussed in initial when you started the course for idealized system, you can similar qualitatively similar behavior you can see here. Another interesting thing here, you can see the potential energy function we have written in terms of like C1, C2 Q, C3 Q square, plus C4 Q plus C5, Q to the power, 4th, something like this. So, whenever you can see the various, we can see this kind of equilibrium path, right, and then on imperfection, this was stable symmetric, and then we have also seen, symmetric but unstable path, right, and right like this. But all these cases, it were all symmetric bifurcation include all the square term and quartic term, q square, q to the power 4, even power term, okay, that is why they were symmetric. But when there is this asymmetric path is there, then it will have this cubic term, this cubic term become important. You see, of course, this has to be quadratic, right, quadratic function. So, these does not really matter. So, cubic term will be present. So, cell buckling involve this cubic term, that is why it is so asymmetry in bifurcation, and because of this cubic term it shows imperfection sensitivity. And what kind of imperfection sensitivity this shows? 2/3 power, half power imperfection sensitivity, half power, right, half power imperfection sensitivity. How do you explain that? P by P critical, it varies, imperfection to the power half, right. So, P is the limit point load, P critical is the critical load. So, with increasing imperfections, the load carrying capacity decreases, right, and it is the notorious imperfection sensitivity, okay. And this imperfection sensitivity that is captured through this present analysis, which is beyond, we have simplified a little bit, but it takes into account the coupling, the coupling between the in plane stresses and then out of plane deflection and things. So, they are geometrically coupled, they are coupled to geometric nonlinearity, okay, and that is what the mode interact, the closely spaced mode or multiple mode interact, and this interaction among different mode is the culprit. See, because of the cubic term, the system itself is unstable and asymmetric, right? Huh? But at the same time, when this closely, so individual modes are basically asymmetric and then imperfection sensitive. Now, both these mode interact. I have shown to you using a simple column, right? Augustus column, interacting column, that where these two mode imperfect and two modes, if they are interacting and they are coupled, then individual mode may be imperfection insensitive, but because of the coupling they will become imperfection sensitive. So, that reduces the load further. So, this kind of cascading effect happen, and that is what is the key to the imperfection sensitivity of the cell. Okay? These are important. Now, I will explain some more stuff, but it is mostly qualitatively. But what happened is that if you do experiment, so in order to reconcile the disparity between theoretical and experimental load. So, what happened that initially it has been a law poses as an enigma to the researcher community, that why there is so much of difference between the theoretical load and experimental load, because the linear theory cannot predict that the interaction among the mode and thing. So, the first analysis that was proposed to explain this fact was by paper by von Karman and Cian, right, by von Karman and T. Cian. I think it is in 1941, and then they have explained this phenomena, okay. And after that, there was subsequent work by others, okay. There have been, and his thesis, von Karman's thesis, which was written in Dutch, okay, later it was translated. So, it went into obscurity or oblivion, but later it was translated to the English speaking community. Then people started realizing that he also proposed, von Karman and Cian explained these modal interactions and then why this disparity of load, these things. But there have been a post-critical theory, post-buckling theory by Coiter, okay, theory by Coiter, okay, Coiter. So, Coiter's name I have explained to you, the imperfection sensitivity, right. Coiter's theory of imperfection, half power, 2/3 power and things, okay. So, he has his basically thesis dissertation written in Dutch language, and later it was translated into English, so that people can understand. Okay, so Coiter's thing. Huh? So, all this contribution basically, so but post-buckling theory of Coiter, that he provided a asymptotic solution to the post-critical regime. What happened is that asymptotic solution means, what happened that means after buckling, there is a huge reduction of load, right? This kind of things happens, right? So, asymptotic means but his solution was valid only immediate to the post-critical, load. So, deep into, for larger deflection, it is not valid. That is what the asymptotic theory is. It is some kind of approximate solution to the nonlinear differential equation. So, it used some kind of perturbation expansion and asymptotic property of the asymptotic series basically. They use a asymptotic series and perturbation of the field variable, okay, to solve the equation, and it is a approximate solution, and it depends on the smallness of some parameter, asymptotic parameters, okay. So, those things has been given by Coiter's post-critical theory, but please, those are very interesting, and then it explains this load drop, okay. So, this was to reconcile the disparate experimental load. There have been this knockdown factor was developed, knockdown factor was proposed, knockdown factor. So, what is the knockdown factor? You see that what we have seen in theoretical load, P critical, so P critical maybe if you see the pressure, P critical pressure, axial, is what? It's a divided by 3 into 1 minus mu square, EH square by R, right? This was the formula. So, the experimental load, P critical, that is phi by P critical, okay. So, this is, theoretical load and this is experimental. So, experimental. They use some kind of factor to reduce the theoretical load to get the actual load, and that factor is called knockdown factor. And NASA, National Aeronautics and Space Administration, they have investigated this widely, and this is based on the huge experimental program. In fact, in around 1970s or even before that, okay. But recently there was a renewed interest by these people to further, keep the margin lower, because the knockdown factor has wide variability, okay. So, there have been some probabilistic analysis also for, based on that what should be the, so reliability based design can be done to choose this phi because of the uncertainty involved. So, the basis of this knockdown factor phi is of course experiment, because people have tested large number of samples, okay. There have been large number of testing program and testing campaign involved, and based on, and this all this phi initially whatever was proposed and adopted, because in space exploration by NASA, they use as very conservative value of this knockdown factor, okay, very conservative, and essentially it took as the, if you do lots of experiment and you plot, your theoretical results are here and then experimentals are somehow here, okay, somehow here. So, what they did, they have taken essentially and lower bound of that experiment, okay, and so that's a huge disparity that to take the and there was significant scatter among the data. In view of this significant scatter, why this significant scatter? Because there is so much of uncertainty involved in the imperfections, cell geometric imperfections of cell. See, here we have assumed something like the, the imperfections which are very similar to the deflection profile, but actually it is not. These are random imperfections, okay. There are n number of imperfections that can occur. So, to be safe in design, they have proposed, NASA has adopted this knockdown factor which are very safe. Of course, later, there have been a renewed interest in around this 2017 or so, even people little around that they have, tried to reduce this, reconcile this, that margin, so that they can have, that will allow economic design, okay. So, along with that, so you understand what is knockdown factor. Of course, knockdown factor are proposed as a function of R by T. I will write down the expression for that. So, this knockdown factor for the cell, so phi is expressed as 1 minus, for cylindrical cell, 0.9, 1 minus e to the power minus root R upon H into R upon H divided by 16, okay. This one is the knockdown for cylindrical cell, knockdown factor KDF, this is KDF for cylindrical cell, okay, for cylindrical cell, yes, So, this is for L by R greater than 0.5, less than 5, and then capital R by H. For this is the range of validity, because most of the experiment has been conducted in this, all the experiment, So, that was basically empirical formula that has been, fitted by NASA, okay. So, this is for cylindrical cell, this formula has been given, okay. So, other than that, let me explain to some other things. So, these are for the design, of course, these are for design purpose, for design purpose, right. Because NASA space exploration involved not only this, all aircraft and other things, but space mission involved this, spacecraft, right, which are essentially made of cell, right, and then you have to be very careful about their design, right. So, what happened in, if you see, The way if you do experiment, cylindrical buckling experience, cylindrical cell buckling, right. So, how it will look like? You see, initially in the simulation, whatever we have learned, that this fellow will buckle like this, right. And then here also, in something like this, So, we have seen that this kind of, what kind of pattern is this? This is a square pattern, right? Square pattern. That is what we have assumed when we simply supported, failed. So, when we assume W is equal to, W0 sine, phi x upon, A, and then sine, sine alpha whatever, sine alpha x, alpha x and sine beta y, right. That when we assume this is for the Poitras solution, we assume like that. So, our buckling mode shape essentially made of square pattern, right. That was our assumption for the solution for substitution in the Donnell equation, right, Donnell's equation. But when you do experiment, you will see hardly this kind of pattern form. The pattern are completely different, and then I will explain why it is so. So, what happened? Of course, this experiment, whatever I am explaining, I will assume that while doing the experiment, it's not that easy to that you are directly applying load, compression load, So, this is subjected to axial compression, right. While you are applying compression, compressive force, from the top, there is a mandrel that is put inside, okay. So that this fellow, so that is giving some kind of loose support to the cylinder. Inside we have put some kind of handle, What happened? No, some kind of this kind of geometry only, maybe a ridge, like a solid cylinder itself. So that gives a continuous support to this, okay, and then you apply this kind of force, okay. Then you will see that as you are approaching, so maybe this pattern is good, this pattern is good until this, you see, immediately until after buckling. But after that, what really happens? If you go little far, then the kind of pattern that is formed. But please note that I am explaining you to what that I am putting a mandrel inside, so that this fellow that is nothing but a cylinder, solid cylinder, that will give a little support to this this one. So, essentially the outer cylinder, the cylinder that is being tested is essentially acting like a sleeve on the top of that. You understand? That is the mandrel, okay. And I am keep on compressing it. So, then ultimately you will see that what happened, I am not explaining much. So, essentially what happened, let me explain to you. So, you see, ultimately this square pattern will convert it into a diamond pattern. Diamond pattern. And this kind of pattern is called Yoshimura pattern. Yoshimura pattern. This pattern is a diamond shaped pattern, and then it consists of these furrows, these are the furrows which is parallel to the perpendicular to the longitudinal axis. These are furrows, these are furrows, and this one, this inclined one, these are called ridges. These are all ridges. Why it is diamond kind? You see that because this one is the furrows, and here are the ridges, right? These and these are the ridges, right? furrows and ridges, huh? All right, these. What happened essentially? So, if you cut this thing, so furrows are going inside and these ridges are coming outside, okay. So, you take a small, Coca-Cola can or a beer can and then you compress it. You will not get exactly the whole pattern throughout the length, but you will get it concentrated somewhere, because that is nothing but the localization of the, that is called localization, displacement localization. But here if I put the strand, this beautiful pattern to form, you have to arrange for that mandrel so that it basically support this, okay. So, that is very important, okay. You get similar kind of pattern in the middle, but that is a different thing, that is some kind of displacement localization. But here what is this pattern is forming all through. What happened, these furrows and these ridges, they are forming. What happened initially, let me tell you. So, if you consider, so I am considering one of the circumference here, then what happened, this. So, if you consider this one, this circular shape, right. So, furrows are essentially, will look like this. So, you see these furrows, the length of furrows, sum of the length of furrows are identical to that of the circumference. So, this represent an inextensible mapping on the surface. So, it represent an inextensible mapping of the surface What? So, this kind of, when you see that circumference will become this kind of consisting of furrows and then ridges, ridges are inclined, these are all inclined. So, this, see what happened is that this, because of this inextensible nature, we can clearly understand this can only happen by bending. So, what essentially happened, this kind of pattern represent that at the end, when it is completely buckled and in the post buckling regime, all the load is essentially taken by the bending. There is no membrane energy. What is membrane energy? I am standing here, you are pulling me, so I am going to, stretch, like out of plane displacement is happening. You see that? That is what von Karman nonlinearity, right? Epsilon xx is half del w del x square. Because of out of plane displacement, there is in plane strain, right? So, membrane strain is, but here the membrane strain is there. So, essentially in the most critical regime, all the membrane strain energy getting converted into bending energy, okay. All the strain energy. So, that is the reason why you see that first loading increases and then it decreases. So, why it is this increase, why this increase is happening? Because initially when you are pushing this cell, the cell is trying to it is trying to deform out of plane, and that through that deformation it is straining membrane strain energy, okay, out of plane deflection, but that is adding membrane strain energy, okay, not bending. But as soon as this membrane strain energy is increasing gradually beyond a particular level of deformation, that will not be energetically favorable, that the bending energy will be energetically favorable, it will suddenly drop to this Yoshimura pattern. You see, understand? So, when this membrane strain energy is happening, that regime of behavior, that load increases and then after that it decreases because of the formation of the Yoshimura pattern. You understand? So, at the end, basically if you go to little deep post critical regime, what happened is that all these these furrows has a tendency to go inward. It has a tendency to go inward, to move inward. Why it is so? Because if it goes inward, then it will have all bending energy, no membrane energy, and that is energetically favorable, right. So, that is the reason why there is a tendency of these furrows to grow inward. And if you see, when you push a cell, you can do this experiment, you take either a Coca-Cola can, you take a beer can, and then you push it, then you will see that you will not get this UFO pattern because you do not have mandrel-like arrangement, but you can definitely see that at the middle there is this concentration of displacement, is localization of displacement is happening, and that there is a tendency of it that it will propagate or move inward. So that it takes essentially the bending strain energy instead of membrane strain energy. Okay. So, pattern formation is not only common here, or localization of displacement is not only common. Please note that all things are elastic here, there is no inelasticity. Okay. So, it is localization, but nonlinearity is there, geometric nonlinearity, right, because localization and all these things cannot happen without nonlinearity. Okay. So, it is not common for cylindrical cell, but in spherical cell also similar kind of things can also happen. Okay. So, I will explain to you a little bit. So, in spherical cell what happened? If you take a spherical cell and then once again, and it is subjected to external pressure, spherical cell, and it is pressurized externally. Okay. Or you can take it, you can use a suction pump to take thing out, so that it is compressed. Okay. There is suction. Okay. That is another way to do it. So, what happens? See, if you consider here, there will be of course the mode shape. If you consider axisymmetric mode, the solution for the axisymmetric mode of baffling is given in the book of Timoshenko and Gere. Timoshenko and that's elastic stability of structure. There is a book by Timoshenko, right? There the solution for the axisymmetric buckling of spherical cell is given. This looks like Pn, S, cosine of beta S, where Pns S is basically the meridional coordinate. Okay, meridional coordinate. So, P is nothing but Legendre polynomial. Legendre polynomial. Polynomial. This is a little more complicated, it is modulated by cosine function. So, if you see the way this buckling mode looks like, it will have this kind of thing, in the equator, in the pole, it will deform like this, and outside this there will be this thing, and but gradually this will come down, Why? Because you see Legendre polynomials are something like this, the variations, if you can recall, the Legendre polynomial, they are decays, right? You see that, right? Legendre polynomial, their magnitude decays with the distance, right? So, Legendre polynomial defines along the meridian, this meridional axis, this will decay. So, maximum displacement occur here at the pole. So, if you just really go little beyond in post critical regime, what happened? Abrupt. So, initially global buckling mode will localize at the top. So, all displacement can be localized. Essentially, we will see that this kind of elastic localization occur in the spherical cell, and that is kind of abrupt. So, post critical. Similar, so this analysis has been presented by various people like Hutchinson and Odoli and others. The analysis is a little more complicated for you to follow unless and until you are conversant with this asymptotic technique and a perturbation technique and things, but it is definitely in Timoshenko and Timoshenko's book of stability that essentially discuss the buckling only, they do not go beyond that. But nowadays with the advancement of the subject, there has been more advanced analysis, especially Hutchinson and their group, and all this analysis has been presented in significant details, and they are very interesting actually. The only problem is that you have to have your mathematical background little, you have to put little more effort for that, but it is a very interesting problem. You see the localization here of displacement, similarly in cylindrical cell also localization happens in the middle. So, the localization problem where you see that the equation has to be nonlinear, and then equation must have a large term comparing the others, then only you can have localization, and then it also allows to have an asymptotic and very nice asymptotic or a perturbation based analysis, okay, to do that localization. Similarly, you can also have conical cell, you see conical cell, because conical cells are also very common in space exploration, right, and these are if they are subjected to some kind of this, and then sometimes they are also subjected to this kind of pressure, and then this pressure can be whatever is coming from the thrust vector control, and these are like sometimes these are all follower force, and for there you can have floater kind of dynamic instability. But if you consider static instability like buckling, there is also some kind of pattern that can form. People have not studied, but you can do that. Okay. So, with this thing I would like to conclude this cell buckling. What I want to emphasize that cell buckling itself is a huge topic, and then it's a very fascinating. Okay. But it's a whole whole subject itself. But if you see that there are many resources, especially the book by Bajjan, the book by Bruce and Almorth, the papers written by Calladine and then Southwell, and then this Cian, and then von Karman, and then the thesis of Poiter. So, all these things gives a very detailed things. There are these phenomena are well known, but there are still things to explore. So, with this thing I will, and there is a group actually of cell buckling research group. So, some of you, if you want, you can join in that group. Actually, there are many discussions happen over there. So, I would like to thank you all for the course, and today is this is the last lecture for that. If I find some of my lectures are useful, maybe there are small mistakes here and there. If you find, you can always mail me to notify me that. But essentially, I have seen, I have consciously tried to avoid mistakes, but human being is are prone to do commit mistakes, and sometimes some misconception may also occur in my mind as well. But nevertheless, you can send your feedback and clarification and thing. And with this thing, the lectures will be put, online and things are comes to be useful for you, that's where I think my effort, I would consider myself rewarded. It is not that how much you have learned, but then the prime aim of the subject was when I started, doing this, that I wanted to have that. Well, it's not that how much you have learned, but the thing is that to give the glimpse of what the subject is, to open the avenues in front of you. I have covered very little. So, I have covered perhaps the tip of a iceberg, but then the whole that subject is there, So, that is what thing, it is what I try to ignite or to inspire you and to ignite the passion in you, so that you can explore of your own. That is more important rather than learning, you see. So, that is all. Thank you very much.